Alrighty, thank you everyone. We are ready to kick off the last session before tea in this room. It's predicative dispatch by David Mertz. If you have been doing Python development for 20 years or more, which some of us have, you know the name David Mertz. He wrote an incredibly popular column in the 2000s. He has served as a director of the PSF for several years. There is 4 paragraphs of bio I'm skipping over. He's done a lot of very, very impressive things. And I would attempt to read the bio for David's talk, but to be honest, I don't understand it all that much. So I'm hoping David can enlighten us instead. So in the interest of David rather speaking to you rather than me, David, let's go.
Thank you so much. Most of you, or many of you, were here when it was scheduled earlier, and we had AV problems, but unfortunately this is a half-hour and a 45-minute talk, but perhaps if people are interested in staying for additional discussion after that half hour, and if they don't walk us out early, I'm happy to go longer, but maybe I'll leave a pause when it gets to the 30 minutes, so people who really do want to get to tea can do so. I have to give credit for the nice background to Steve Young, who designed. A number of people have used this, but mine have a bit different style for the remainder. So the idea here that I'm going to be talking about is essentially I'm going to try to get you to rethink much of what you have learned in computer science classes. In particular, it's across diffusion logic, and I'm going to introduce you to this module, this library I wrote called Gnosis Dispatch. And I think it's great. I think you should use it. But even more than that, I think that I want to urge you to reframe and rethink some of the ways you've thought about both issues of type systems and issues of flow control. And I think that in many ways they're more closely related than they're often treated. And in particular, I think we should do some more flexible things than we commonly do in object-oriented paradigms or in functional or in general procedural paradigms by adding a few conveniences and a few different ways of thinking about things in Python than might be as familiar. I should say a brief word. I'm at work right now. I'm very fortunate to work for Service Employees International Union, one of the largest and most progressive labor unions in the United States. And they're so kind as to pay for me to be here, but they're also just wonderful people to be working for, doing very worthwhile and good political things. I'm a principal engineer, so I do technical things within that context, but they're wonderful. One of the things, and it's more an opportunity to have the slide than anything else, is the main project I work on is essentially just a data ingestion kind of system called Ada, where the locals, the 150 locals that are members of our union of 2 million people, will send in data about the membership, and we process it and normalize it and things like that. But I didn't make them in Ada, and I got to use this other automatic tracker rooms for automated processes, which don't use the library I'm going to talk about, at least not currently. So here's the way I'm going to set up an example. And then I'm going to get into some more geeky, mathy, technical stuff as a sort of second delve into it in some more detail. But imagine that you're a group of developers, perhaps at some organization, like a public service organization kind of thing. And you want to have these various methods that tell you things about nations and, for various kind of comparisons or other purposes. And maybe you'd like functions like income and morbidity and exports and demographics I mentioned. Obviously, there could be many others. But you want a certain kind of standardization across all the different 180-ish nations in the world, where you would answer a similar question, but the way that you would have to go about answering the question is very different in each case. Data comes from different places, maybe different kinds of processing is necessary to get suitable outputs from these various implementations of similar calls. And one way you could do that is you would probably very often think of making some sort of object-oriented framework. You'd have some superclasses that work on, nation or something, and then you'd implement children, and have methods like these, and the methods would do the corresponding things. That's okay. I mean, obviously, most of the people in the room have done that sort of thing, and it works. But I think it's a little bit inelegant. I think there's a better way to go about it. So imagine, the organization here has published this module. It's called World Data, and it has these capabilities about inquiring about various information about the various nations. And this is set up using this dispatch module in particular. And the way it works is it has a bunch of capabilities built into it, but it also emphasizes extensibility of the same API as more people have improvements or additional information they can provide. So in this hypothetical nations namespace that we're importing from the World Data library, I want to define a number of additional implementations of the same functions. This one demographic that I mentioned is hypothetically one such function. And whoever created this initially had implementations that pertain to many nations in the world, but in particular, they maybe didn't have information about South Africa, or they didn't have methods, API keys, whatever was relevant to obtain the information. So perhaps using this technique, we want to extend it ourselves. It has already this, hundreds and hundreds of implementations, but it doesn't have one where the argument to the demographic is a place object, and I don't know what that object is exactly, but it's some sort of class, and it has methods, and it has attributes and things like that. And in particular, this particular kind of class has one attribute, ISO 3166, the standard abbreviations for various nations. There's a 2-letter and a 3-letter version of the abbreviations in the standard. And so what we're stating here in the first implementation that I'm adding to the overall nations namespace is that if it so happens that the argument you pass into demographic is one of these place objects, that's a data type, and this place object has an attribute ISO 3166 whose value is ZA, then do this implementation. And the stats for South Africa is a real URL, but I have no idea what the organization within it is, how they provide information. But presumably you'd need some credentials to get data from the various places, and you'd navigate to locations on it. And so this isn't very much code, but this is the idea of how you would more concretely implement it. But then maybe similarly, we also are lacking in our nations object information on the demographic of Lesotho. And in that case, though, we're going to do this other implementation that takes a different type of argument passed into it. It takes a string, which is just the word in Lesotho. And here we have not just the data type, the fact that it's a string we're passing in, but also this predicate, the fact that it is a string, but it's that exact string. And in such a case, the way that we would implement that functionality is different. We would talk to this hypothetical database that Lesotho maintains, and we would have certain user and password and other information about obtaining the information. And then in each of these cases, we would return this demographic data, whatever the details of it were. But maybe we want to even be more specific about it. That's fine. Maybe we pass in the name Lesotho and there's some default kind of demographic information that's returned, the database APIs and so on. But actually, there's also many different agencies or organizations or governments or UN or other things that also provide information. And perhaps for certain purposes, we prefer one versus the other. And so we're going to create yet another implementation of this same function, you notice each, of course, is decorated by this @nations namespace indicator. And in this case, we would do it differently. If we wanted the UN version of the data or the African Union version of the information, we would do something different to obtain it. But we here have gone through and I think, plausibly, I haven't actually implemented these things, to find different ways that we would want to call this demographic function and use different kinds of programming logic, different kind of credentials, different kind of resources in order to obtain the information, and yet they're all the same function name. In this particular case, you may have noticed that the signature that I gave before in the prior instance was just a string that's equal to Lesotho, but in the second implementation, we also add a second argument with a particular data type, and that, because it has more information about the pattern of the call, it will be chosen in preference to the other one if that additional information is provided. So I think that's a bit magic, and I also think it's a bit cleaner than, this hundreds deep chain of inheritance of children from the various ways we would implement demographic, and likewise for the other functions that we talked about. So we've implemented this. We've object-oriented inheritance. We've downloaded the module for the world data, and it came with a whole bunch of implementations of a whole bunch of functions, and we just added a few more. So now, either we're contributing this back to the overall project, or just within our own internal use in our own organization, we have these additional capabilities attached to that same namespace or object. Dispatcher is another word that I'm going to use to describe it. And we could just get a string version of it, and it would say that hypothetically this nation's namespace has 16 functions within it, but there are, I just made up a number, of course, but this 1,348 implementations. So for each of these 16 functions that pertain to information about a particular country, there are many, many implementations, presumably because there are many nations about which we would want an implementation. And this is truncated. You see there's ellipses in the middle, but if you call this describe method on the namespace dispatcher object, we get a summary of what has been implemented and in what conditions it will be called. So somebody, like the providers of the module that we downloaded, provided an implementation of the income function that would take a first argument that's place, but it would be some kind of thing that had an attribute called name, and that name was Algeria, and it would return appropriate information in that case. And then we see what's numbered number one in the income function. It's the one that we just implemented ourselves to add with these ISO 3166 was equal to ZA, and it would go about performing the code in some other manner. And ellipses, because there's 1,300 here hypothetically, but then likewise we would have these couple of implementations of demographic and perhaps many more that we got with the library, and we would have these various patterns that would indicate that this was the particular implementation that was of interest, whether simply it's a string that is equal to Lesotho, or whether it was a string equal to Lesotho, but it also had some alternate authority, like the UN, where we were getting data. But in all of these cases, we have these one function, in a sense, that has many, many implementations that are sensitive to the kind of information that you're passing in. And I think this is a flexible and extensible way of organizing code. Now, what I'm doing here is in many ways the same as function overloading, which is available not in Python, but in a number of programming languages. So here's an example from C++. You don't have to know C++, I'll walk through it very briefly, but I also think it's a pretty simple example. we've implemented this function called volume, and there are several different implementations, and they are taking different kinds of arguments with different data types. So we can get the volume of a cube or a cylinder or a prism, but it's not so much like in the name of the function, and it's not that you couldn't create a function that got the volume of a cylinder where the arguments have to be integers, but just to indicate that the types of arguments can cause the same function name to be called with a different implementation based on those types. This is what C++ and other languages do. So when we call the same name, vol, it looks at the data types that are passed in and it decides which implementation it wants to use on that basis. So what I'm doing is analogous to that. And here I'm just running it. I've compiled that program and I run it and you get the various outputs so you could calculate those and they're correct. So function overloading is a limited case of multiple dispatch. I mean, it doesn't. We really are looking at the types and the number of the argument and calling the same name in a different implementation based on that. So that's a thing that exists in some common programming languages. But the other part that I want to talk about is when we think of type systems like that in C++, we tend to have a really limited and stereotypical concept of what a type is. And so we think of types, often in statically compiled programming languages as, these things that follow the architecture of the computers we tend to be working on. So, an unsigned int 8-bit and int 32 and float 64 and complex, et cetera. And all of these names, these happen to be in Golang, these particular spellings, but it's very similar in many, many programming languages. They really are historical accidents of the ways that computers were built. And I mean, it's not bad the way computers were built, but bytes don't have to be 8 bits, and words don't have to be 4 bytes, and computers don't even have to be binary; they can be trinary or something else. But these particular accidents, motivated accidents, but these particular details of how hardware has developed has given us an overly reified idea of what it means to be a data type. And that is reflected in many programming languages. And it doesn't have to be that way. I'm not saying it's a bad thing, but we can think about it more flexibly when we want to think about what it is our programs are actually trying to do. So this is mysterious Haskell, which the people were here before the other one didn't happen. I mentioned is, I stared at the code for a very long time, figured out how to write a few lines there. But this is defining a new data type in Haskell. We're going to do the exact same thing in Python in the next slide. And so we'll be done with other programming languages in just a moment. And this defines a data type that's called small int, which here means a number between 1 and 100, rather than, 0 and 2 to the whatever power of 2 power. And in this case, I decided in my implementation of the initializer for the data type to clip when a number that was passed in was more than 100. We could have a different implementation. That's up to us what we want to do. But the point is you can't initialize one of these small ints except for as a value between 1 and 100. And you can see on the little sidebar, I run those Haskell program and we initialize with some various things. And in one case we truncate, and then in the other case we raise an exception because we're saying, that type just simply doesn't know how to deal with that initialization value. So let's do the exact same thing in Python. It really is pretty darn close to what the Haskell is doing, but probably more familiar to most of the people in the room. And it's a little more verbose. But we can define a class in Python. It's going to be a subclass of int. So we are inheriting capability that was, comes with the language. course, in Python, ints are unlimited length, so we're not quite in the same world of 2 to the 32 versus 2 to the 64 kind of thing. But then we take a look at, whether we really are trying to initialize it with, an existing int, and if that number is negative, we raise the exception. If it's more than 100, we flip it, just like we did in the Haskell case, and we get this new kind of object called a small int in Python, and then we can run that, and we get the same kind of results, that we either just take the number as is because it's fine, we clip it, or we raise an exception. So this is an okay data type, and it says something more specific about the kind of data we're interested in working with within this type than just saying it's, a 32-bit int. We could add other conditions, of course, to this. We could, define prime numbers, and we only accept those as initializers, which is call ahead to what I do later in some of the examples. Now, just initializing the data is something, but it doesn't do all that much. We probably want this is all still like sort of living in the object-oriented world, which I'm going to move away from in a couple more slides. But we probably want to do something with these small ints, this new data type that we've created. Like maybe we want to add them together to each other. So if we want to do that, we have to implement more methods. In the case of Python, these magic methods, these dunders with the double underscores that will exhibit the various behaviors that we think is appropriate for our new data type. So if we add a small int, something else into a small int, we'll call the superclass, which is doing what int does to add, but then cast it back into being a small int. And you can see what happens here that for some cases where we're adding a small int 25 or small int 30, that's still a perfectly typical small int, and those are the results 55. If we try to add something larger, we wind up with the clipping or truncation behavior. And what we haven't implemented, for example, is the radd method. So on the left-hand side, there's a plain old int, and we add a small int in. We don't do the truncation anymore. We don't clip. Now we can define an radd method, we can define a null method, we can define all the range of arithmetic operations that small ints would want to participate in. This is just showing how we might go about it. I think I've already said it, but the thing I want to emphasize is that at its heart, putting aside the sort of accident of what's convenient to do on existing computer architecture, what a data type is really just a collection of predicates. Int16, various languages like C or Go or Rust or whatever, is just some integral value between negative 32,768 and positive 32,767. And I mean, obviously it has other predicates. When you add two of them together, it creates a ring. And, there's a variety of sort of algebraic or topological rules about our expectation of behavior of these things interacting with each other in various ways, but those are all just predicates about how this object behaves. So I think that we can bypass a lot of that. We can, if we have this mindset where we're thinking of types are simply objects that fulfill predicates or collections of predicates, then let's skip some machinery. Let's not define these classes and subclasses and children and hierarchies and method resolution orders and multiple inheritance and things like that. Let's just express the data types as predicates directly. Here's a few functions, and this is a bit mathy, and the rest of the examples are going to build on this, but I have more complete implementations than I do the thousands of missing functions about nations and obtaining data about them. I have here several functions that have something to do with asking whether a number is a prime number. And there's an implementation that is called isSmallPrime. Of course, in this case so far, these just all have different names, these functions. And they'll work within their expected domain. So in the isSmallPrime case, we already have just in a file on disk, it's in the module if you download it, a collection of all of the prime numbers that are less than, 64,000 something. And there's a fair number of them, but they're not too many to just put in the data file, which is what I did. So checking for membership in that set of numbers is very fast, and that's probably the best way to check for something being a small prime number. For a medium prime number, we just use those same primes that are stored on disk and check whether they divide evenly into the number that's potentially a prime, as long as that number isn't more than 2 to the 32nd, because we're only looking at the one prime numbers up to 2 to the 16th. There is another way of checking primes that's called the Miller-Rabin pseudo-primality test. This is a bit of number theory stuff, but this is the way that people actually generate large prime numbers for like cryptographic purposes, like ones that are thousands of digits long. The thing about it is a probabilistic algorithm. You do a certain number of iterations of it, and it will identify a number that is definitely composite, but you have to run it a bunch of times, and every time you say we can't prove it's composite, then it becomes more and more likely that it's actually prime. And it does actually give you very reliable answers, but not 100% certain answers. So therefore, we could have another implementation, this one called Agarwal-Kyle-Saxena, or AKS later, which is a really clever number theory math thing that these mathematicians came up with like 20, 25 years ago, that will, in polynomial time, tell you whether a number is prime with certainty, like even the one that's thousands of digits long. No one ever uses AKS because it's still much slower than doing Miller-Rabin. Miller-Rabin is good. And just to throw in another one, I have this other function called Gaussian prime. And there's a certain way, which I don't need to explain what it is, where it's meaningful to talk about complex numbers being prime or not prime, composite. And Gaussian prime, you can see, takes a complex number as an argument that gives you this answer to whether it's that kind of thing. And I mean, this is fine. You can check what kind of thing it is that you're passing into this, combined is prime function. And we're doing a couple things here, though. The first thing we're doing is checking for a type in the conventional sense. Complex is a type of number, int is another type of number. And, in the one type, we're calling this particular implementation. And maybe, we didn't create those implementations. We imported all of those implementations from somebody else's library where they've done these interesting numeric things. But in the other instance, what if it's an integer? Well, there we want to evaluate a variety of predicates and call a different function depending on what kind of integer it is. So this is a way we can structure our code. It's, you've all written code much like this many times. It's also closed. Like, I wrote this function, I give it to you. If you wanted to deal with other cases, you have to change this code or just rewrite it in your own code or whatever. But it's, it's a closed object. 5 minutes? Okay, I am definitely going to go over. People can leave, but yeah.
But we're entity, so you can go over it.
Feel free to leave, but anybody who wants to stay, I'm only cutting into tea time, not into another time, so I don't feel as guilty about it. Plus, I like to talk about this. So we can imagine recasting this again, and we have our implementations of these various priming kind of things that we got from somebody else. And imagine there's something more complex than just is prime, but some substantial functionality that we don't write ourselves. And maybe we want to arrange it so that we create a bunch of things like the small int, medium int, complex number. And we want to do the switching solely based on the type. We can do that, but we have to do a bunch of work of creating all of those different types. We can do it. I mean, and this is a little different than we saw before because the limit is a little bit different. Can't include 0, but in concepts, it's very similar to the between 1 and 100 that we looked at before. Okay, that's fine. We have that type. And as long as we're within that type, we can do the switch based on the data type. It's again closed and not extensible. We don't need to go through this in detail, but it works. You create these instances of the different types, and the numbers are prime and not prime, and you get appropriate results. But I want to show you the other way to do it. And this is in many ways just repeating what I did with big nations, but I've sort of given you all the details and all the mechanism, and I think it's somewhat motivating, only somewhat, because checking for a prime isn't like the most important. Well, it is for some purposes, but you're going to write much more interesting programs. So what we're doing here is we're importing from Gnosis dispatch, from dispatch.dispatch, is get dispatcher function, which is a function factory, or a dispatcher factory. And so we're creating the namespace that we're interested in here, nums. We could call it something else, but the point is we can call it whatever we want. And then once we've done that, we can add a whole bunch of implementations to it. And the idea here is that we express both the data type and the predicate right in the signature of the implementation that's of interest. And here, if it's up to a bit bigger, but this one, well, there's a couple differences. This is defined as definitely an int. This is any type, so we haven't given a data type, so it's not going to be as preferred. But of course, if this predicate can't be fulfilled, we have to consider some other implementation. But also, this is going to refuse to do things that are too big or that are negative, etc. And just to show that there's various syntax we allow, you can use the simple decorator, but you can also use this decorator where you're saying what function name you want to bind in. So the actual name of the function we're defining is mr prime, but we want to bind it to the name is prime. It's very considerate. And this has some various annotations, but one of the things we've added is a confidence. I mentioned that Miller-Rabin is probabilistic. So maybe we just need to be that certain of what we're going to get is prime. We'll do some more. We'll go through it quickly, but we have this other function, AKS prime. And the difference here is this is, for big numbers like Miller-Rabin is, but we want the confidence to be exactly 1. So we're expressing that predicate about, which is of course a floating point number, the argument. And a Gaussian prime, same idea. This is again just another way we could use it because the Gaussian prime function we saw before already gave a data type in its signature. We can just wrap it up this way without having to have a body underneath. And just to show we might have more functions inside this namespace, I've also implemented is twin prime. That is 2 primes. They're just 2 apart from each other. And it's, a very simple definition, but it's based on using the same namespace and is prime, and the number that's 2 more or 2 less. But in particular, in the hallway conversation, this is like predicates all the way down. The particular implementation that's going to be used for this call depends on the size and the type of the number that we're calling for. And this is a different function, but it likewise, will do something. So we see the summary of what we defined. In this case, it's complete. It's not the thousands of others that I'm just stipulating might be there, that I've actually done all of them. this is the kind of summary that we get. We find out that there are bound implementations. So is prime has an implementation that satisfies this predicate, or this predicate, or this predicate, or this one, and so on down. And at the bottom, there's also the is twin prime, which has a certain signature. And then I could go, the rest we can go through pretty quickly, and maybe there's time for questions a little bit, but like, what are we doing if it turns out that we pass in something that's not an integer? We didn't actually declare a type for the one that's the medium-sized primes. And maybe we want to do something with a floating point number rather than just do the same check. Like, if it's a floating point, it's just false. It's not a prime. That's up to you. I mean, 3.0 is like 3 in Python. So what is appropriate for your purpose is up to you. But the point is that I can add to this namespace by creating this new implementation that deals with this new case that I hadn't thought of initially. And the next bunch of slides are just a bunch of calls to it where we give various numbers and we call and get a true or false value, but we use a different implementation in each case depending on, this is just, which one is this? Oh, you get false positives of one of them, that's not important. And in this case, we use the Gaussian primality, and it can be true or false, and twin primes and things like that. It's going to raise an exception if it doesn't have any implementation to deal with it. So none of the implementations will deal with -1 as number being passed in. What do we have here? That's the idea. I mean, I have this really obscure footnote. Like, there is a way that, like, mathematicians know a hell of a lot more than I do, define primality of quaternions or things like that. There's actually a way, the Hurwitz primes, which are different from Gaussian primes over complex numbers. So there's like all these other potential implementations that we could be interested in, but I don't have to understand them and know about them to publish my, my anonymous dispatcher, and other people can add to it, but they can also use it just calling that very same function name. And presumably, it's not going to be that one function, it's going to be these 100 mathematical functions that they are interesting for people to use. And then they can extend any of them the same way. Someone did ask me this in the hallway. There is a namespace issue. So technically, if in your type declarations or in your predicate declarations, you need to use like a function that's evaluated for the predicate, or you need to use a brand new data type that, I didn't know about when I created the numbers dispatcher or, the nations dispatcher or whatever. You just have to tell it like, hey, here's another kind of object, or you can initialize the dispatcher with other objects that are currently in scope, and then it'll know how to deal with those things. But the one thing is that you can dynamically add them. They don't have to be here where you create the dispatcher. At any point you can say, well, by the way, there might be this other type of thing that we would have to think about when we're making the decision.
Well, not getting to press a button and it sounds good.
This is my summary. I think that's pretty much what I've said. I think that in many cases, using this kind of approach, especially for large, extensible programs, can be clearer and more expressive than existing paradigms, or more commonly used paradigms. I'm not the first person to ever come up with this idea, but I do think this is a good implementation, and most of the others are for versions of Python.
Oh, I'm going to say thank you. That was absolutely fantastic. Turns out I do kind of understand it, although I was getting hideous flashbacks from some of those mathematical, algorithm names I was thinking of. I don't remember that, and I'm glad I don't.
There's a lot more than I understand in there.
Got it. Do we have any questions today?
Yeah, thanks. Very interesting and great. something that strikes me about this approach is that it's very much in the sympathy of like the insight of that the code is read a lot more than it's written.
Yeah.
And so in the same way that implementations are probably used a lot more than they are written, or you hope.
I agree.
And so something that's great is that, you're doing that. How well does this play with tooling that's, things, some of the new tooling that you get in IDEs, etc., in terms of knowing
That is a very good question. So there's something I didn't mention, but I should. You actually need this line at the top of everything if you're using Python 3.13. I haven't tested Python 3.14 in the 2 days or 3 days since it's been out. I think you can drop this line then, but type checking software like PyWrite or PyType or MyPy or others which you may be using that I've neglected to name, will basically complain vigorously about, where's an example of, like they'll hate this. Like they'll say, okay, int, like rate that, I know what that is, that's a type. And they'll say, what the hell is going on with that ampersand there? Which, logically makes sense to me. It's like, it's an integer and this thingamajiggy. And most of them will probably complain like, well, n is undefined. What are you talking about? That's not a thing that exists in this scope. But in 3.13, and I think even 3.12, maybe even 3.11 with that annotations, from future and import annotations, it treats whatever is in the annotation as a string that's not evaluated when it's compiled to bytecode, but is only addressed later on. That you can evaluate it manually with some things in the typing module. I forget where it is, but there's some capabilities to force it to be evaluated for type checkers. Well, what I do is just evaluate the string. I parse out where the ampersand is if it occurs, and is this actually a type, and is it a union type or basic type, and does this look like a predicate? And you could have and this and that and the other thing. So you could have multiple complements of the predicate. So today, every time I've written these things, I put, type ignore at the end of all these lines so that my editor will shut up about complaining about it not being correct. But it still runs. The type checking tools just don't like the way it looks. But given that that's all static type checking, not runtime, it actually doesn't make any difference. But my hope is that for 3.14, when you have by default annotations or strings, the type checking tools will catch up and stop complaining.
It's just about definition, right?
Yeah, exactly.
Thanks. Very nice talk. Would you be able to do something like a predicate that's like
Oh yeah, absolutely. So, maybe you don't want n greater than blah, blah, blah. You want to call is big n or something like that. And then obviously you have to implement is big somewhere. But that's where, as I showed in the other slide, you're going to have to make sure to put is big into the namespace that the dispatcher knows about. But you can always add that later. It doesn't have to be when the dispatcher is created. You can just add it whenever you want. So I intend to use my function is big as part of a predicate. I'll just throw it into the namespace.
So you could switch on this prime.
Yeah.
So it's called extra types, but it would also have a function, right?
Oh, you can have anything. It's just any object that exists, put it into the namespace where the dispatch decision is made.
Extra objects of example. It's really nice presentation. Have you considered maybe, as crazy as it sounds, like writing it? Honestly, I love the syntax, and I would really kill for something. It's like, I'm a big fan of match statements and
Yeah.
that sort of thing. And I feel like they're in the right direction, but it's almost not enough. And I often run into the problem where you can see someone wants to do something like this, like someone, and like they'll beat a match they'll beat it into shape. That's ugly and it's like difficult to parse. But
Yeah.
this is like clean. And you know, like someone else's module way down there doing stuff. Then in my module, I just want to extend it here. I just want to like this extra function, little extra functionality in there.
So about 12, 13 years ago, there was a lot of discussion in the Python mailing list about multiple dispatch and that being included. Not the predicate part, but at least the multiple dispatch. And many people, including me and Guido and a lot of other people, wrote implementations of multiple dispatch, which is a couple hundred lines of code. It's really easy. I mean, that was way before we had nice decorators or annotations, so it wasn't nearly as pretty as you can make it now. But in concept, you could do it. And I think there was a PEP, like a long, long time ago, before things were different then. And basically the resolution was in the FuncTools module, we got single dispatch, which will switch on the type of just the first argument, because the sentiment at the time was that covers most of what people want to do. And there's actually some pretty complex issues if you try to switch on all of the different types. I mean, that's a little different than the predicates I'm talking about, but like, which takes priority? Like if you have a function that's a int b float and a function that's b float a int, and you pass in, you know, two integers, which implementation do you want to call? I mean, assuming you treat int as some type of float, which isn't really, but close enough. Those aren't questions that's impossible to answer, but they are questions. In the version I wrote a multiple dispatch, 13 years ago, had like a whole bunch of decision strategies that you could choose. Like, I want to do it lexicographically, I want to do it in this weighted way, I want to do other things. I love this in real Python. I feel the odds of success of a PEP are low, but you're going to help me write it.
Sorry, guys, I'm happy to keep taking more questions, and I'm sure David is as well, but I just want to note that there's 1538 week well into T. T is supposed to end at 1545. So if you did want to go for coffee or something, your chance to do so is rapidly closing. However, I'm more than happy if you want to keep asking questions of David, or as it's standard, you know what he needs to we can find him and ask more questions afterwards as well. I think in the interest of just basically letting David get some tea, if there are no further pressing questions, I think we'll pull back. Thank you very much, David. That was absolutely fantastic.